All right, when we want to apply stretches and shears to multiple points, we can put all of those points into a matrix and then perform our matrix multiplication. So T1, this is a shear, and it's a shear parallel to the x-axis. So T1 times my square of points, 1, 2, 0, 1, and now I'm going to put all my points in, all the x's and y's. Of course, you could do this individually with each point, but much better to do a matrix. So now I'm going to get my new set of points. So 0, 0 is going to remain fixed, and then 1, 0 is going to remain fixed. Remember, points on the x-axis are going to stay the same. But now I'm going to have 3, and then with that point I will have 1. So my y coordinates again are going to stay the same. And then I'm going to have 2 and 1 again. So if I plot these points, I can see, I've done that down here, I used GeoGebra. So here's my original square, and here's my shear. So all of my points shifted horizontally for points off the x-axis. The area of this parallelogram is 1. The area of my unit square, of course, 1 by 1. So area of this is equal to 1. If I look at my first transformation matrix, the determinant of T1 is also 1. So I've got area of my square is 1, area of my shear is also 1, determinant was 1. I'm going to repeat this process with my stretch. So T2s, 3, 0, 0, 1. All of my x coordinates are going to be multiplied by 3. So 0, 3, 3, 0. My y coordinates are going to stay the same. So if I look at what happens here, now I've taken my square and stretched it into a rectangle. I've got 3 by 1, so the area is 1. Old area is 3. Determinant is 3. So my area of my square is 1. Area of my stretch is 3. So this seems to imply that the area of the transformation, I'm just going to call it transform, is the determinant of the transformation matrix times the area of the original, and that is true.